Hello everyone. Just figuring a few things out, so it took me 2-3 minutes. So how is everything going on in MLT week 3? Did you take a look at the content so far?
Yes, ma'am.
Yes, ma'am.
Okay.
Yes.
All right.
So, ma'am,
Yeah, Viraj, go on.
I have a doubt in practice assignment. Can I ask it now?
Where do you have a problem?
Ma'am, in question number 4, practice assignment.
Practice assignment. We'll cover that. Just stay on hold. We'll do that. Okay. All right. So can I have a raise of hands by those who have watched the lectures so far? Just I want to get an idea. Okay, good. All right. Okay, good. Sure. Thanks. All right. So let me share my screen.
Excuse me, ma'am.
Yeah, Srishti.
Ma'am, could you please explain in this session what is the relation between the correlation and the data point cluster centers?
The correlation
And the cluster centers.
yeah, sure. This question, I'm seeing a lot of noise. This question is from graded or practice? I mean, if it is in practice anyway, I'll be covering it today.
Ma'am, in general, I want to know the theory regarding that, how we find that
All
is
right.
there a correlation.
Yeah, sure. I'll cover that. Sure. Okay. Okay, can you see the question screen? I'll start then.
Yes, ma'am.
All right, thanks. Okay, so what we are going to do today is we'll take up the activity questions and then practice questions. We'll take them one by one, and if along the way, if you have any doubts, we will cover them. So that's how we're going to go. So Srishti, you asked me something, so probably I should cover it now so that you don't stay on hold. So what did you ask? What is the relation between correlation and cluster centers, right?
Yes, ma'am.
Okay. So if I remember correctly, the question might be if there is a, okay, I don't remember what the question is, but if you want to consider the correlation of that is existing in the data points and you want to figure out whether that will have any effect on the clusters or not, so we can talk about that. So let's say x1 and x2, there are two features in the data. So yeah, x1, x2, let's take x1, x2 only. So for every data point, we'll have two values, right? This will be our data. So x1 on the x-axis, x2 on the y-axis we have. So if you plot these data points, let's say the correlation between these two is, let's say, 1. So in that case, what will happen? If x1 increases, x2 will also increase. If x1 decreases, x2 will also decrease. So that's the correlation which tells what is how the values in x1 are varying. What is the effect of the variation in the values in x1 to the values in x2, right? What's the relation? So let's say the values are like this. I mean, that's like perfect correlation. This is like perfect correlation. So if you would plot them here, this is 2, this is 2, this will be a point here, and then for 3, 3, there'll be another point, and so on for 4, 4, and so on. And the kind of line that you will get will be like this. So let's have the points only so far. So these are the points that we have. This is our data, right? Now, what is the question regarding the clusters you were asking, right? So let's say these data points have some inherent clustering among them, something like this, right? So after you run the any clustering algorithm, let's say there'll be some cluster mean over here, another cluster mean over here, and another cluster mean over here. So since the correlation between the features, which is x1 and x2, was 1, all the data points lied along one line, and hence what are the cluster means? They are the means of the data points themselves, right? So they will also lie there on the same line only, right? So I think that's the question, right? If there is if the correlation is 1, the cluster means will lie on a line, right? Is that clear?
Yes, ma'am. And ma'am, if it is 0, then what happens?
So the correlation can be, positive, and it can be negative, and it can be 0. So 0 means there is no correlation, which means if x1 increases, x2 may reduce or it may increase as well. Okay, so let's talk about negative first. So negative means if x2 increases, if x1 increases, x2 reduces, and vice versa. So let's say, so you're basically sorting these two values, and then you're comparing. So let's say they are opposite like that. I'm just taking the opposite to explain you. I'm basically taking the same example so that you get the idea. So it's like this. So when you sort them out, when these values are reducing, these values are increasing. So it's an opposite association that we have. So it might be a perfect negative -1 association, right? A correlation. So that this example is a positive correlation, precisely +1. And this is an example of a negative correlation, precisely -1. And 0 means there's no correlation, which means the points could be somewhere, anywhere in this region. Okay, and then in that case, you would not be able to say anything about the cluster. Firstly, you need to see whether clusters exist in such a data or not. That's one thing. Secondly, given just this information, you would not be able to say anything about the placement of the clusters, right? Here, the data is very clean, so you can really comment about the placement of the clusters. Okay.
Okay, ma'am. And ma'am, can the data it also can be in decimals also, not a perfect correlation, 1, -1 or 0?
Yeah, of course. So -1, it can be between -1 and 1. Yeah, of course, it will be any value between them. It could be, let's say, 0.2 minus 0.2. It could be 0.3. It could be 0.485. So in practice, actually, in any real world data which has noise in it, you would never get a correlation like these. Okay, so these are the practical values of correlation that we really encounter in real world data. Okay.
Okay, ma'am. Thank you.
All right.
Ma'am,
Can
one
you
question.
mute yourself? There's some noise from your side, Srishti. Yeah.
Ma'am, one question here. Can I
Yeah,
ask?
sure.
Using correlation. Yeah. So, what is the geometrical meaning of the correlation? If we say that if the some correlation of the two data is the 0.2 and the two data is the 0.8. So, what is the geometrical meaning of this?
All right. So we had taken this example of two variables, right? So geometrically, if you see,
Yes.
let's continue with the same example, then I'll take a different case. So here what was happening, x1 and x2, we are trying to see the correlation amongst these two features, x1 and x2. And if they are varying in the same direction, which means if x1 is increasing, x2 is also increasing, and then another value you see x1 is increasing, x2 is also increasing, and so on, which means the line, if you draw a line or the line representing these points, will have a positive slope. Okay, if you want to look at the geometrical interpretation, this will be positive slope. Now let's take a look at an opposite example. Let's see this one. Yeah, let's see this one itself. So 102. Okay, let's plot it, and I'm just putting some approximate points. So 20 and 3. Okay, then you have, let's say this is 20, let's say this was 100, 20 and this was your 2, right? And then 20 and 3, and then 4 and 4, then 3 and 20, right? 3 somewhere over here, and 20. My points are not in the right measurement, but when you actually put them in the right measurement, you will get a line like this, which is reducing, which is having a negative slope. Okay, so this gives you an idea that as you increase the values of x1, the values of x2 will reduce. This is a negative correlation. And this example you've already seen, where there is no correlation amongst the values. So they could be randomly placed. You would not be able to get such association. Okay, that's a geometrical interpretation.
I had one example like that. One data set is varying through the x, another is exponential of x, and another set of the example is one is x, another is logarithmic of x. And
Okay.
Since I have taken the both examples such a way, because it is the inverse of that each other, so it is the equidistance from the y equal to x line. So x and e to the power x and x e to the power log x. So both spreaded something data is there and both is increasing.
Right, they all will be increasing, so they will have a positive correlation.
Yeah, that is fine. What's that about the quantity of the correlation? Like that, it will be 0 to 1. So which one will become below the 0.5 and which one will become below above the 0.5? Is that correlation, the magnitude does matter somewhere?
Okay, so in this case, see, the quantities are actually increasing, right? So it will be a it will be a higher correlation. If you want to see the range, it will be definitely between 0.5 and 1. It will be
Yes.
closer to 1, because actually it will never happen that x is increasing and e to the x is decreasing, right? So the the relation between them is always going to stay the same, right? If one increases, the other also increases. So there will be a high correlation between them. Okay.
So one, okay. Something whenever it is going so much high, we are getting the something zero correlation, and one we are getting the zero correlation, and one we are getting the something different correlation. In the e to the power x, we are getting some different correlation. So is it how actually it is work?
Yeah, so what you can do is you can see the formula. So you will actually get to see how much variation happens when you vary some value in x, how much variation happens in e to the x, or any if you look at logarithmic value. So the correlation value will try to capture how much variation will happen when you make some change in this quantity, how much change happens in this quantity. Okay, so here this is a perfect +1 correlation. Here it is a positive correlation for sure, but how much variation happens, you can actually check that out using a correlation formula. Okay, this is actually easy to plot also, and we can see how the line will definitely have a positive slope, but it will not be x is equal to y slope, like x1 is equal to y1 slope. It will not be like that. It will not be a 45 angle. Some other angle will be there, but definitely positive slope. Okay, so that will
Hello,
decide
ma'am.
how much correlation will be there. Yeah.
One thing here that if we see these cases from a large scale, then it might seems like both are perpendicular to each other, kind of. So, uh, will it be a strong correlation?
Sorry, which is
Like
perpendicular?
log x and e power x, in large scale, these are can be visualized as kind of uh, perpendicular, because
And
log will not increase uh, after after a certain value.
right. So the thing is, the value with which a quantity will increase is not same, but one thing is for sure, that it will increase, right? It will never happen that one is increasing and the other is reducing, right? So that is why the slope will always remain positive. But looking at the exact values of x, looking at the exact values of e to the x and the exact values of log x, that uh, those values will decide how much positive correlation should there be between these quantities. Okay,
Okay. So positive correlation, that is for sure, but
that is for sure. Yes,
yeah.
right, because
Okay.
like I told you the rule of thumb, one is increasing, the other is also increasing. That is always going to happen. So it will be a positive correlation, but the amount of correlation will be decided by these actual quantities. Okay, is that
Ma'am,
clear?
I have a situation here. Like, can I ask something?
Yeah.
Let's say, ma'am, I have the data points lying in the line y equals to 2 and y equals to 4 along
Okay,
the line.
y is equal to this is 2.
Yeah. and y equals
Okay.
to 4 maybe.
Okay,
So all the data points like lie along this line uniformly, along
correct.
the lines. So what will be the clusters formed by this Lloyd algorithm in this case?
Lloyd algorithm, k-means you
Yeah,
mean?
when k equals to 2.
Yeah, we will cover this just now in some time. This, I think this is a part of a practice assignment, right?
Ma'am, you were
This is
discussing about all the
related assignment.
questions, so I just asked this question here itself, so if you can clarify.
Okay, so this is actually a different scenario. So here, firstly, some initial clusters will be there, right? Cluster means will be there, right? So it depends on the distance between these two lines. It depends on, what is the length of this line. So let's take an extreme case. These are the points and these are the points. So if you run Lloyd's algorithm on these points, this will be one cluster and this will be another cluster. On the other hand, if let's say you have points like these, let's say points like these, okay? Now, in this case, if you run Lloyd's algorithm on these points, you might probably get clusters like these, okay? So it depends on the distance between these and the distance between these, and it also depends on what will be the initial clusters that you will initialize. So it's actually a good exercise problem which we can try it out. Probably I want to do it in the next session. So what we are going to do is we'll be doing some code and we'll take some data points and we'll see how the output of k-means varies with respect to different inputs. So I plan to cover this in the next session. Okay.
Ma'am, there was a concept that professor taught in the lectures that the cluster separator will be perpendicular bisector of the points joining the mean of the data points.
Right. Yeah.
Is it true?
Yeah, that is true. That will definitely be true in this case as well. So if you want to see that here, so let's say this is one cluster, this is another cluster. So let's say this is your mu1 and let's say this is your mu2. So when you join these two means, right, and the perpendicular bisector will be this. So this will be the perpendicular bisector of this cluster and this cluster. Okay.
Yeah.
Yeah, so that is going to stay true in this case as well. So that's fine. So we can take this up in the question that is connected with this very concept in a while. Okay.
Okay.
All right. So let's get started, and along the way, if there are any doubts, we'll keep covering them so that we get some idea of what all you have understood and what you have not understood. So what I have started off with, I have the first question in the activity questions, first video. How many configurations are possible for 100 data points into 10 clusters if these clusters are allowed to be empty? So how many partitions are possible? Any idea?
10 per 100.
K raised to power n.
K to the n, right? So I hope this is clear to everyone. So let's say, so let's take the general one. There are n points and there are k clusters. So if you look at each point one by one, we'll look at each point. This data point has an option to go to any of the k clusters. So the options that this data point has are k. Similarly, same goes for the other data point. This data point has also k options and so on. So every data point has k options to go to. Please note, we are allowing that the clusters are allowed to be empty, which is not the case in k-means clustering. So whatever we will get out of this will be actually an upper bound. Okay, so this quantity, you multiply all of them, so you get k to the n, right? So if there are 100 data points and you have to divide them into 10 clusters, right? So k to the n, 10 to the 100. These are the possible clusters that you can have if you allow the clusters to be empty. In k-means, we want all the clusters to have elements. So this will be an upper bound. Okay, so yeah, 10 to the 100 is the correct one. Next question, a cluster will be good if the points in the cluster are far apart, the points in the cluster are close to the mean, homogeneous, heterogeneous. So what will be correct here? Any ideas?
Close to the mean.
Close to the mean, correct?
What is the meaning of homogeneous here?
Yeah. Yeah, homogeneous, heterogeneous basically mean same kinds, right? So homogeneous is actually a generalized term, but in this context, we are talking about data points, right? When would the data points be homogeneous? When they would have similar values belonging to the two features. Let's say we are talking about two features here. So don't get confused with this terminology. Please let me know if you want me to change it. So here we are talking about, this is one feature. Let me call them feature 1 and feature 2, right? So these are my data points, feature 1 and feature 2. So homogeneous means if there are points here and if there are points here, so these are the points which have approximately this value of feature 1 and approximately this value of feature 2, and these are the points which have approximately this value of feature 1 and this value of feature 2. So they all are close to each other, and that indicates that they are similar. Okay. On the other hand, if you look at some other kinds of points, so these points are scattered around, okay, and they have a different value of feature 1. So if you look at this point has a different value of feature 1 and different value of feature 2. And if you look at this point, let's say this point has a different value of feature 1 and different value of feature 2, which is different from this point. So these 2 points have different values of both the features. So we would call these 2 points as heterogeneous. On the other hand, all the points which are falling here, which are close to each other, see, this is data. So homogeneous, heterogeneous, they are very generalized terms. They can be applied in different scenarios. But here we are dealing with data. So in the context of data, how can we say that 2 given points are homogeneous or not? If they have, so this is a data point P1 and this is another data point P2. We obviously would look at these values. If they are, similar, then we can say that P1 and P2 are homogeneous. If they are far apart, then we can generally say that they are heterogeneous. Okay, is that clear?
You are talking in terms of correlation, if I'm not wrong, like because
no, this is not correlation. Correlation means one is increasing, the other is also increasing.
No. Actually, what I'm asking, because you have marked this red point over there, and now like you are asking, upper one. So now you are saying they are closer and similar value, but in what terms, in what scenario you are talking about the similar values? Because the values are different in these 2 points which you are marking as homogeneous also.
These points, is it?
Right.
Okay, let me take 2 points here. This point, okay, I hope you can see it. These 2 points I'm taking. Okay. Now, if you look at the feature 1 and feature 2 values of these, please pardon this bad notebook, but if you look at the feature 1 and feature 2 values of this point, let's say P3, and if you look at the feature 1 and feature 2 values of this point P4, this will be somewhere here and this will be somewhere here, right? Both these values are similar. I mean, they are close by, right? That's why we can say that these are homogeneous. Whereas on the other hand, these 2 points, the red points that we looked at, their F1, F2 values were quite different, far apart. So we can call them, they're heterogeneous. Is that clear?
Okay. Now I got it.
All right. Okay, so here, the second option, the points in the cluster are close to the mean of the cluster. So if you look at these points, if you find the mean of this very cluster, and if the points are closer to the cluster, we can say that they are homogeneous, right? On the other hand, if let's say this is the mean, let me use some other color. Let's say this is the mean, and you're looking at this point and this point. These points are far apart, right? These points are far apart. So this is something that we do not desire in a good cluster. Okay. this point is already clear. So these two options will be correct. Let's look at the next question. If Z1, Z2, Zn represent the clusters assigned to data points x1, x2, xn, which of the following would represent the mean mu k of cluster? Well, here it should be k. I will get this fixed. Okay. Which of the following would represent the mean mu k of cluster k? Okay. Is this terminology clear to everyone? Before we start answering this, can somebody tell, is there any doubt in this terminology? Yes?
No doubt.
No doubt, is it?
Yes.
Okay, okay. So what we are given is x1, x2 up to xn. We are given these points. For each point, we have a cluster indicator, z1, z2 up to zn. Now, these z values will be any values from let's say, how many clusters? It's not given. K clusters are there. So these z values can be any value from these. Is this clear so far before we move on? Okay, I assume it's clear.
Yes.
All right. So,
Ma'am, Z, sorry, I had a small
yeah,
question.
go on.
Z are the boxes, like these are the clusters.
No. These are not the clusters. So clusters will be formed from the values of these zi's. That's what I want to make clear. I mean, let's have everybody on the same page before we move on. Clusters will be formed from these z values. Let's say I have this. Let's say there are 3 clusters, 1, 2, 3. So zi's will be something like 1, 1, 2, 1, 1, 3, 1, something like this. Okay, for each value of xi, there will be a value zi, and zi can be any value from 1 to 3. Clear
Okay,
so
they
far?
are indicating the clusters. They are
Correct.
indicating
Cluster
of the
indicators.
cluster numbers.
Let's note it. Yeah.
Got it.
Yeah. So the clusters will be formed from these elements. So whichever element has 1, that all will be one cluster. I mean, you can roughly look at like this. This also will be there, right? Something like that. I hope you get the point. So this is what we have now. Which of the following would represent the mean of cluster K? Okay. Given a cluster, let's say it has some points. Simply put, forget about this notation. Mean of this cluster C, how would you find out? Tell me. Mean of this cluster. There are some points. So
the
these
data
are
points which are in the cluster divided by the number of data points.
correct. Sum of data points falling in this cluster divided by number of data points, right? Okay. Now getting back to this terminology, mean of cluster K is what we have to find out. Okay, there's one thing. This one is actually indicator function. Are you aware of indicator function? This one. This is called indicator function. So in this you will pass a condition. If the condition is true, this will return you 1. If the condition is false, it will return you 0. That's the indicator function. Now here what we want to find the mean of cluster K. Firstly, we need to see which all data points have been assigned to the cluster K, right? Yes or no? We need to see which, these are all the data points. From these data points, we have to see which of these have been assigned to the cluster K. Now, how do I know which cluster has been assigned to X1? That is Z1. So, if I write Z1 is equal to K, mu of cluster K. So, if I write Z1 is equal to K inside the indicator function, this will return me 1 if the cluster of first data point, which is X1, is K. If the cluster of first data point, which is Z1, is not K, it will return me 0. Okay. So this is what we will need to use to find the mean of the cluster K. That's one thing. Now, we need to check this for all the values, right? We need to check this for all the data points xi's. So when you find the mean, you told me this formula, sum of all the data points. So numerator, we are looking at sum of all data points xi, right? I goes from 1 to n. This much is should be clear. But this is not all data points. We are only interested in those data points whose cluster is K. So what I'll do is I will bring this term here. So I'll write indicator of Zi is equal to K. So what this means is, x1, if the cluster of first data point is K, x1 will be added. Let's say the cluster of second data point is not K, that will not be added because this will be 0. Let's say the cluster of third data point is K, that will be added, and so on. So this becomes your numerator. Denominator is going to have how many such elements, how many elements are there in the cluster K. Now, this very thing, if you add this up across all the data points, this will give you, this will precisely give you how many data points have been assigned cluster K. Are the numerator and denominator clear so far?
Yes. The numerator is the distance from, like, for example, x1, when you say x1 plus x3, x1 is the distance from the mean?
No. x1 is the data point. So let's say 1, 2, 3, let's say this is the setup. So 1, 1 is a point, let's say, and then 3, 3 is another point, and let's say 1, 2 is another data point. So this is my, let's say, x1, x2, x3. These are the points, and I will be finding the mean of these data points. Of course, what will be the mean? Tell me. The mean will be 1, 1, and 1, 2, and 3, 3, correct?
3.
Yeah,
Yes.
sum them up. Right? And then divide by the number of elements. How many elements are there? 3. Whatever that comes out to be, you can see that. So somewhere over here, wherever that is, that mean will lie. So xi's are the data points, not the distances. Is that clear? Yes or no? All right.
Yes.
So now quickly let's take a look at the option. So now this is the initial setup. So that should be clear to everyone. So since we have done it already, so you can see that the last option is the correct one, and every other option is weird. It doesn't make any sense. You can see for yourself that they will lead to any weird thing that is not going to be. So the last time you see that the numerator is xi's, all xi's summed up from I goes from 1 to n, multiplied by the indicator variable. There should be bold that indicates a indicator function. So I'll get that fixed. Zi is equal to K, and denominator is going to give you the number of elements belonging to the cluster K. Okay. So the last option is going to be the correct one. Let's move to the next question. Z1, Z2, Zn represent the clusters assigned to data points x1 to xn. This is clear to everybody so far. Now mu k represents the mean of cluster K. Okay. Which of the following would be a good measure for goodness of partitions? So now what we're talking about is, let's say we have some partition. Let's say we have some data points here. These are the data points that we have. Let's say we put them in one cluster, and let's say we put them in another cluster. How can we say by a given, obviously visually you can get some idea, but you need some number to tell how good these clusters are. So what we are talking about is goodness of clusters. Okay. What we are also given are the means, right? This is mean, let's say mu1 for cluster 1, and let's say this is mu2, mean of cluster 2. This is what we are given. Now given this setup, if I ask you, how can you tell that these clusters are good? or how good these clusters are. If you can give me some number, one number if you can give, that tells me something about the goodness of these clusters.
Distance of all the points in a particular cluster to its
Correct.
mean and summing.
Correct, very good. So what we can check is, see, if in a cluster the data points are scattered. On the other hand, if in a cluster the data points are like very much together. So this is scenario 1 and this is scenario 2. So we obviously see that this is a good cluster and this is not a good cluster, because the points are scattered around, here the points are clustered together. So how can we say that this is bad, this is good? We can find the mean of this cluster, we can find the mean of this cluster, we can look at the distances of all the points from the mean and so on. Okay, square them up, sum them up, we get some quantity. Obviously that quantity for this cluster will be huge and that quantity for this cluster will be small. So for a good cluster, that quantity is small. For a bad cluster, the quantity is large. So that's one measure that we have, which we can continue using to find the goodness of clusters. Okay, so that's the setup. Now what we are asked here is, what will be a good measure of goodness of partitions? Okay, let's look at the options. Xi minus mu I. Does this seem fine? What does mu I mean?
Mean.
Mean of what?
Mean of a particular cluster in which this xi is present.
Okay.
No, but this
So
is mean of xi.
yeah. So let's see. So xi goes from I to, so it will be I is equal to 1 to n actually. I goes from 1 to n. That is fine. But does the mu go from 1 to n?
Mu, no.
Mu will go from from where to where? 1 to k, correct?
K, yeah.
Very good. So here, this is weird term, right? Mu is going from 1 to n. It doesn't make any sense. Okay, let's see the second one. Xi minus zi. So let's start putting the values. So if you put I is equal to 1, you actually get x1 minus z1. x1 minus z1, what does that mean?
Z1 indicator.
Correct. X1 might be some, let's say 2, 3, right? 2, 3 minus 1. Does it make any sense? No. Right? So this is completely incorrect. The last one, xi minus mu of zi, right? Xi minus xi, this let's say 2, 3 minus mu of zi. Mu of z1, let's say z1. What is z1? 1, cluster 1. Mu of cluster 1 is what we are saying here. So this cluster 1 will have these elements, and these elements will have some mu, which we are representing by mu of z1. So that mu of z1 we will subtract from this term, and that perfectly makes sense. And we do that for all the elements, and we sum that up, and we have to minimize that term. That is a good measure for goodness of clusters, right? That's what we talked about. Is this clear?
Yes.
All right. Let's move on to the next one. Tell me, does k-means always converge?
Yes.
Okay. Does it always, is there any question? One moment. I don't know what this is. Anyway, so there will be, yeah. Are the clusters produced by k-means optimal?
No.
Why?
Not always.
Because we are not sure, means this k means will stop at local minima. Means it hovers around 3 conditions. Means we will not, maybe we cannot reach the global minima, means
right. Yeah, that's correct. So what is the objective here? The objective is to minimize the objective function, right? So whatever we just now saw in the last question of the previous the previous question that we saw, right? The distance from the mean should be minimized. Sum it up over all data points. That is precisely the objective function in k-means, and we have to minimize that. Now that could follow any particular pattern, right? That could follow any particular pattern. So let's say, so it depends on the initialization of the means, right? How do we start k-means? We assign some initial clusters, cluster means, right? That is a random allocation that we do. Let's say we gave some allocation which gave objective function. There's this objective function we got from that random allocation, and we ran few iterations, and finally we settled over here. After this we will not move because we have reached the minima of here, minima of the objective function. So this will, the algorithm will converge over here. Okay, but we see that the global, yeah.
Ma'am, my doubt is that we are forcefully stopping in this algorithm to stop here. Yes, no?
No, the algorithm construction is such that
it will stop here. Means,
obviously, it has to stop somewhere, right?
Yes,
any algorithm you write, that has to stop somewhere, right?
Yes, that means we are not going to all combinations, because it will take more time, or means it will be.
Yeah, definitely. We are not going to all combinations. If you go to all combinations, getting back 10 to the 10,
100.
k to the n, right?
Yeah.
That's the upper limit. If you want to go to the all combinations, so here there were only 100 data points and only 10 clusters, but in practice there'll be millions of data points, right? In practice, the data that you get will have millions of data points, and if that is in the power, even if you want 5 clusters, 5 to the power million, right? You can imagine the total number of possibilities that you might want to check if you want the global minima, right? This doesn't make sense. You will not actually end up getting anything. So what k-means is presenting is an algorithm that gives us a decent result. In practice, it gives us a decent result. So it doesn't matter even if
yes, that's my point, that we have made this algorithm in such a way that it stops at a local minima, whichever the first local minima which it encounters.
Yeah, right. So it basically follows a path, right? It starts from some initial assignment of means, and then that results in some value of objective function, and then in every iteration we keep changing the clusters assigned to different points. If they are not in a cluster whose mean is closest to them, which means if there is some other cluster mean which is closer to them, so they will keep moving from one cluster to the other, and when they all are happy in their own with their own means, it will stop, right? It makes sense.
Yes, means here happy means that next, if we go to the next iteration level, suppose we move from t to t+1. So in t+1, the objective value of objective function will be greater than the previous one. So we will not move.
No, it will be, yeah, okay. Well, in the scenario, which scenario did you say? When, no, this scenario is actually not going to happen because everybody is happy. If you move a person who is already happy and you make it unhappy, the value of objective function will increase. Correct?
Yes.
Correct? Is that clear to you? Yeah, go on.
During the proof of convergence, sir talks about t+1, like how he said, when the algorithm is reaching a local minima. In practically, the data scientists, like sir said, the t+1 would be lesser than t, and if t+1 is more than t, of course we have reached some point of convergence. Do data scientists actually go for more iterations of t just to check if the minimum, I mean, if they reach
in that case, you will actually, the data scientists will keep moving on, and there won't be any point to stop. So according to you, what should be the point of stopping here? So
that's what I'm saying. Is there an optimal solution that you say, okay, fine, I've done 100 more iterations, or what do people actually do in the field?
Okay, yeah, all right, that's a good question. So what you're asking me is, you start with some, you start the k-means, which will initialize your means, some initialized means, and that will lead to some clusters, right? And there would also be an associated value of objective function. Okay, this is one run of k-means. obviously many iterations are there. Many iterations, right?
Right.
Okay. So in practice, what happens, like I said, when you start from some initial means, it might be possible that you end up in a local minima. So what you do in practice is you will start this k-means, let's say some 10 times. Okay. So in the first run of the algorithm, let's say you started with this initial value of means, and in some next run of k-means, probably you start with this one. When you
Hopefully,
start,
we'll reach a good objective function. That
yes, you do actually
on an
reach
average
it.
you would.
Yes, on an average you would. So this is your global minima. So in this particular run of k-means, you actually reach the global minima. So you keep doing it for 10 times, and you also keep a track of the objective function value that you get in the end. So whichever run of k-means gave you the minimum value of objective function is the one that you are going to go with, because that's your global minima. Is that clear?
Yes,
Hopefully.
Yes. So this is what we'll study in the coding session, next session that you.
Okay. So the thing is, in coding we would be doing from scratch. But whatever you asked me what happens in practice, right? So this is a part of MLP course where you would make use of sklearn library. And if you read the documentation of k-means in sklearn, there are some parameters. For example, there's a parameter which tells how many iterations do you want. So let's say, so we know this k to the n is the upper limit, right? Obviously k to the n is like much upper limit, because it also considers empty. So it stops much before this. But even in that case, let's say it stops in 20,000 iterations. I'm just giving an example. Let's say you do not have that much time. So you can also mention that something like n is number of iterations that you want to run k-means on. Let's say you mention it to be 5,000. Okay, which means wherever you settle in 5,000 iterations, I'm fine with that. So this is the cluster configuration that I'm getting in 5,000 iterations, and I'm okay with that. So that possibility is also there. And how many times you want to run k-means, that option, that there is a parameter for that also. So that you can see. If you want to dig deeper into it, you can check that out.
Yes, ma'am. One thing I have to ask is that in this programming part, in the code, there will be a code which will say that if the objective function in the next iter is greater than stop here.
If the okay.
Because we are hovering around three conditions. One is the previous one. Means one is the present, in which it is computed with its own and with its neighbors, and next one is that it assumes that
it assumes what?
It assumes that in another cluster the position is better. I can go there because the distance is becoming less. So we assume and we calculate, and the last is that let's suppose it has gone there and many points have shuffled. And in this current situation, after this shuffling, let's say this is t+1, and in this objective function is lesser than, okay, we will go. But if it is greater than previous one, then we will stop there.
If it is greater, why would it be greater? See, what is the rule that we are following for in every iteration? What is the rule that this is the construction of k-means itself? This is what k-means, how k-means algorithm works. So what we do is, in every iteration, we compute the distance of each data point from its own mean and the other means as well. If there is some other mean whose distance is smaller than its own mean, it will be assigned to that new cluster, right? So that's how we are functioning, because by doing this, the value of objective function is going to reduce, correct? This is how we are functioning. So what you're telling me is sort of dynamic programming. So what k-means is sort of following is a greedy approach. Are you aware of greedy and dynamic in some course that you do?
Yes.
Right. So then it should be clear to you. So you can say that k-means is sort of a greedy, follows a greedy approach, because it has a greedy objective that whichever move will reduce my objective function, I'm going to go with that. But it might happen that probably that was not a good move if you look at it from a global perspective. So dynamic programming kind of situation I mean, checks all possible combinations, even
yes,
if
yes.
it is it,
Now
right?
yeah, right, ma'am. I have understood. That means we will not go there. We will reject that and
Completely. Yes.
Yeah. Okay.
Yeah.
I understood. This.
All right. Okay. So getting back, yeah. So this is clear to everyone that the solution provided by k-means is not always optimal. Okay. Next question: which of the following are true? K-means algorithm automatically determines the optimal value of k. Tell me.
No.
Right. So k in k-means is a parameter that has to be supplied by the user. If you talk in data science terms, k is a hyperparameter. So hyperparameter is some parameter that has to be passed by the user initially before building the model, right? So before you start k-means, you need to supply this value of k. There is no way that you give the data and you ask k-means to somehow automatically figure out the value of k. It is not going to happen. You have to decide. So I think sir also gave one example. Let's say there's a teacher and the teacher wants to assign some grades to the students. So in that case, he might be sure that A, B, C, D, E, let's say 5 grades he wants to assign. So he will give the value of k to be 5, and accordingly the algorithm will function. So, but in some cases we really don't know the value of k, and we might need to try out different possibilities, right? Okay. Next is k-means algorithm cannot automatically, so this is the correct option. Okay, it has to be provided as an input parameter. Next one. Finding optimal cluster is an NP hard problem. Is that correct?
Yes.
Right. We just now discussed, right? It's an exponential, 10 to the millions. It is never going to be finishing execution. It's an NP hard problem. But k-means helps us find a solution to an NP hard problem, right?
No.
Yes or no?
Yes. Means what? K means help us find solution. NP. Yeah. Solution. Yes.
No, it doesn't. It does not find the
solution. Means it may not be optimal. Means but.
Yeah. So this is a little tricky, but I hope everybody is clear here. K-means actually does not help us find solution to the NP hard problem. It gives an approximate solution. It gives a solution which is not optimal. So it's not that k-means is solving an NP hard problem for us. Solving an NP hard problem is not possible. So we cannot find any algorithm that can solve an NP hard problem. We are getting some approximate solution. So that's how we function in practice, right? A traveling salesman problem and all these problems which do not have an solution because they are NP hard, we manage with an approximate one. So that's how we function. All right. Next one, if in an iteration T, the distance of a data point from the mean of its currently assigned cluster, ZIT, is the least as compared to its distance from means of the other clusters, we do not change the cluster assigned to this data point in this iteration, right? This is clear to everyone, yes or no? We just now discussed. Okay. Now, what is true? This implies that ZIT will be the final cluster assigned to Xi, and its cluster will never change in any subsequent iteration. Is that true? Is ZIT going to be the final cluster assigned to Xi? Or the other option is, it may change in some subsequent iteration.
It may change in some subsequent iteration.
Right. Is that clear to everyone? Because in some iteration, this point did not move, but in subsequent iterations, there'll be the means will change for different clusters. Then it might be possible that this particular data point Xi gets a mean which is closer, and then it might move, right? So the cluster assigned to xi may change in some subsequent iteration. Is that clear to everyone?
Ma'am, but how will the mean change?
Okay, the means for, okay, so see, this point did not move, but other points would have moved, right? When other points moved, so obviously the means of all those clusters which got affected will change. The cluster from which the point moved and the cluster to which the point came, the means of both the clusters will be affected. Once they are affected, probably this xi gets a cluster which is near now. Okay, so in some subsequent iteration, the point might move, even though it didn't move in this particular iteration. Is that clear?
Okay, ma'am. Thank you.
Yeah. All right. Okay, so next set of questions. Consider a bunch of points. Which of the following would represent a point V whose sum of squared distances from the points is minimum? Anyone?
The mean of those points.
Yeah, the mean of those points.
Last option.
Which is the last option. For the points x1 to xl, so what you will do is you will sum up all the points and then you will divide by the mean. You will divide by the total number of elements, which is L. So 1 by L, and yeah, this is the last option is the correct one. Okay, next one, for data points x1, x2, xn and partition z1, z2, zn and mean of kth cluster mu k, which of the following represents the objective function? Firstly, you tell me, is the objective function in k-means or Lloyd's algorithm a minimization function or maximization function?
Minimization.
Obviously, right? We have discussed minimization. We have to minimize something. What is it that we have to minimize? We have to minimize the distances from the means, right? For each data point. So there could be some k clusters, right? Let's say 5 clusters are there. So for each cluster, there is a mean. For each data point, we have to find its distance. In the other cluster also, for each data point, we have to compute its distance from their mean and so on. This we are going to do for every cluster, right? And then what we are going to do is, we will sum up these. All these values, we will sum up. Some values will come from here, some values will come from here, 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 and all of these. We will put them together. That will be the total value of the objective function. Is that clear? Is
Yes.
that clear? Okay. So here in this terminology, what will be the correct one? So minimization are the second and fourth options. Here we see xi minus mu of zi, and here xi minus mu of mu k. Which one is correct? We just now understood the terminology. It's B. Why?
Check.
Yeah, why?
Zi is that index that means
Correct.
in which we are comparing with basically index with Zi. So it locates its own point in that cluster.
Correct. So if the terminology is clear to you, you can definitely answer this correctly. So that's why I wanted to make sure this is clear. So xi is a point and the cluster assigned to xi will be zi. Now this zi is not a cluster, please note. So you can't write mu of zi. You can't write that. Okay. So zi will have some value from 1 to k. So mu of k you can't write. Yeah, sorry. Mu of k you can't write. Mu of zi is what you will write. What is zi? Zi is the cluster assigned to xi. So xi minus mu of zi is what will give you the distance of each xi from the mean of the cluster to which xi is assigned, right? So this very term will take care of all these distances. Is that part clear to everyone? See, that's a very general term, xi minus mu of zi. and this single term will take care of all these distances. So this is actually writing, let's say this is cluster 1, 2, 3, 4, 5. So whichever point is assigned to cluster 1, whichever point is assigned to cluster 2, whichever point is assigned to cluster 3, and so on up to 5, whichever point is assigned to cluster 5, this very one term is taking care of all these terms. You know why? Because this 1 is given by Zi. Here 2 is given by Zi. This Zi is a cluster assigned to this Xi. This Zi is a cluster assigned to this Xi. Again, Zi is representing the cluster assigned to this Xi. So this 1, 2, 3, 4, 5 is everything is captured in Zi. So we can simply write mu of Zi. Is this clear or not? Is this clear to everyone? This is just the terminology. I mean,
Yes.
yeah. All right. Okay, so the second option is correct. Next one, if the value of the objective function strictly reduces, what does that indicate?
Partition cannot repeat.
Right. So let's say there was some partition. This is one partition. This is another partition. And this will result in some value of objective function. The value of objective function reduces in some iteration of k means, let's say this point moved to this cluster. Okay, that will result in some other value of objective function. One thing that we know is the value of objective function will always reduce. Why will it reduce? We have spoken about it. I'll repeat it. The objective function will change only when there is a reassignment. And the reassignment will happen only when a cluster is found a nearer mean, which means the distances will reduce only, which means is objective 2 is lesser than objective 1. Right? Now, objective 1 became objective 2. That happened when this point moved, which means the cluster, the partitions have changed, right? So if the value of objective function strictly reduces, it indicates that the partitions cannot repeat. You can never get back to the same partition. Why? Because in every iteration, it is going to reduce only. The values of objective function are going to reduce only, and this is with respect to partition 1, this is with respect to partition 2, and so on. Since the values are not same, these values are strictly reducing, they are not same. These partitions will also not be same. Okay. Now, since these partitions will not be same and we only have a finite number of partitions, which is k to the n upper limit, this is basically what tells us that the k means will converge. There is never an going on and on thing that can happen in k means. Okay, is that clear? Any doubt so far?
No, ma'am.
All right. Next one, choose the correct statement. There are only finite number of partition configurations. There are, in fact, we just now discussed it. There are a finite number of partition configurations. Okay. All right. Next one. If mu1 and mu2 are means of two clusters, then for all the points settling in C1, the means mu1 and mu2 are equidistant. The mean mu2 is closer, mean mu1 is closer. Which one is correct? Very straightforward question.
C.
Simple, right? Mean mu1 is closer than mu2. That is why these data points are there in C1. Next, for every cluster, its Voronoi region will be formed from intersection of k minus 1 half spaces if k is the total number of clusters. Let's take an example of 2 clusters. So if this is a cluster, let me not draw this. So there's a cluster and this is the mean, mu1. Mu1 is the mean of the cluster 1. Let's say mu2 is the mean of the cluster 2. Okay. For every point that belongs to cluster 1, we just now discussed first question. For every point that belongs to cluster 1, mu1 will be closer than mu2, right? Same goes for mu2, C2. For every point belonging to C2, mu2 will be closer than mu1. So what is the boundary between these two? You join these means and divide them in the middle and put a perpendicular line. This is basically half space. So if this is the entire space, this line will divide the entire space into 2 parts, half space 1, half space 2. That's the boundary between these 2 clusters. So any point which is here will belong to mu1, any point which is here will belong to mu2. Okay. What are we asking here? Yeah, so this was the case for 2 clusters. If there are more clusters, if there are k clusters, there will be k minus 1 half spaces. Here there were 2 clusters, so p2 minus 1, that is 1 half space. This is the half space.
Yes, ma'am. Yeah, ma'am, if we can, sir in class said in this 3.4 lecture that sir considered a case in which their data points are on 2 circles.
Okay, yes. Yeah.
In that case, how a line will be drawn? Because in that case, mean will be same for both the circles. Means that data points.
Yeah. All right. Yeah.
How a line will be drawn? Because line formula is that this x transpose mu2 minus mu1. In that case, mu2 is equal to mu1.
Okay. So what are you asking? You're asking
how means a line passing through the center. How we means what? How we can draw that line? Means
all right. Yeah. My
how
question
we
to
can
you.
get that line?
My question to you. How would k? What do you think? How would k means cluster these data points? How would k means do this? What kind of clusters would you get if you run k means on such a data? Can you give me some guesses, some ideas?
In that case, that mean will be same. So what will happen is that these inside data points will remain there, and maybe that outer data points will come closer because there are 2 means. If we consider either the algorithm will not proceed because of same mean if it does not include equal to sign in that inequalities. So in that case, the algorithm will not proceed, or if we consider the equal to sign, then the mean will be same. So outer data will come inside.
Yeah, Mahesh.
Yes.
So these means are what we are assigning. Please note what you are telling me. There's some gap here in your understanding. What you are telling me is the mean of this cluster is this, and the mean of this cluster is also this. So there'll be some issue. You're telling me, right? Is that what you're telling me? So please note that means is what we are assigning. We are in control. The data has been given to us. We have to see which means to start with. These ones, or probably these ones, or probably these ones. Now, my question to you: if you run k means, okay, I don't think that's clear to you.
Yes, ma'am. I think I got your point that we will start with a random assigning of this means.
So I'm putting these 2 in different colors. If you run k means on this kind of data, it is not that k means will give you this green points as cluster 1 and these red points as cluster 2, this is not going to happen, because this is how k-means function. How k-means functions is what we are seeing just now. Let me get back to this and then I'll go there. Okay, so how k-means functions is, so let's say there are three clusters. So you join the means and then put a perpendicular bisector there, put a perpendicular bisector here. So these three regions will be formed, right? These three regions will be formed. This is another region and this is another region, right? It will be like this. Here what we are seeing, this is sort of concentric. If you run k-means on this kind of data, you will never get such clusters, because as you also told me that the means, what will be the mean of these, the means will coincide, right, in such a setup. If you look at the means of these two clusters, they will coincide, and that is something that doesn't make sense as per what we have understood so far about k-means, isn't it?
Yes.
Right? Okay, another thing to note is that the clusters, so the kind of shape of the clusters in k-means is, you can say, spherical. So if this is the mean of one cluster and this is the mean of the other cluster, all those points which are within this area will belong to this cluster. All those points which are within this area will belong to this cluster. What about these points? So that's basically the perpendicular bisector that we have been talking about. That's where it comes from. Okay, so the points which are on the left of this line will belong to this, which are obviously closer to mu1, and the points which are on the right hand side of this line will be closer to mu2. So that's the kind of geometrical shape of the clusters that you can expect from k-means. Here in this case, the data is such that k-means will not be able to efficiently cluster them. So this is non-linearly separable, you can see, right? This is the kind of separation boundary that you can see between these two data points. If you want this to be in one cluster and this to be in another cluster, this is not a linear separation. So in such cases, you use kernels, right? Kernel k-means is what you use. So in that case, the trick is you basically apply some function, some kernel function on this kind of data. So in this kind of data, on this kind of data, if you apply some kernel trick, let's say, let me mark these points as, let's say, 0, -1, -2, let's say 1, 2. Let's say I use polynomial kernel trick. So basically what that means is you square these points and you square these points as well. So this is 2D and that will result in 3D, right? So these, let's say this is 0, -1, -2 as well. Okay, when you square these points, they will be small values. And when you square these red points, they'll be larger values, something like this. Okay, so now in the higher dimension, these points have become separable. And now if you apply k-means on this data, you would get this perpendicular bisector, right? This perpendicular bisector you would get, and now everything will function fine. So it depends on the kind of data that you're getting. In some cases, k-means might not be able to give you good clusters. Okay, is that clear?
Yes.
Ma'am, one question is there. The diagram you made that.
Yeah.
Can you ask? Yes. Yes. To separate this situation, you made it a higher kernel, means a higher degree. Why don't we make it lower the degree this instead of making higher dimension? We can also separate.
No, you tell me. So this is a 2D data, right? So
yeah,
are you suggesting bring these down to a lower dimension?
No, yeah. I'm not taking. What you did, it made that higher dimension, no?
Yeah.
So I'm telling not making higher dimension, keep it same dimension.
Okay.
Lower the degree of the data. So in that way, our dimension will be also get reduced, and I will get the separate thing also, because what the idea is to tell that means in any Cartesian system, suppose XY line is there, no? 1 degree in the any dimension of the situation, the single degree always make a hyperplane line or the any plane. So 1 degree of the equation, 1 degree of the data in the XY plane always make a line, linear line. And the degree, if I will make a higher, like that y equal to x or 2x plus 3, always create a line because it's a single degree, no? If I increase the degree like the quadratic or the polynomial, then it's become the curve line. Even a square is the multi-degree, no? Is degree of 2 equation, because it is the 2 circle. So instead of making the dimension higher, I'm making the degree lower. So whatever the point is given in the 2 circle.
What is the degree here? So this is actually a sort of circle, right? X square plus y square is equal to some r square. This is the equation. Now, what are you suggesting? How would you reduce the degree so that you can get the separation?
Right. So every x and y is that some square level of the thing. So instead of making the square, I can reduce the every point by the square root using this formula. So every point, data point has the 2-dimension point, no?
So this is, let's say x, this is, let's say y, right?
Right.
For every point here, you have x and y,
Yeah, x comma y, no? So x comma y distributed such a way, it's follow the circle, no?
Correct. Go on.
So it is obviously follow the 2 degree of equation, because if you see that x and y, so somehow I can take it in the 1 degree. Okay, then it will become the line only. So it is.
No, you tell me. So I gave you, I showed you what I'm doing, right? And that is resulting in a separation. So you tell me what should I do? Reducing the degrees, what you're suggesting, right? So what should I? Let's say this point we are talking about. Let's say this is. Let's say this is 0, 0. This is not. This is different, but let's say this is 0, 0. And let's say this is 2, 0. So what should I do?
So here is the lots of points. So remove the center, whatever the circumference of the data is there, no 2,
this one?
Okay. Yes, I can reduce something a square root way. So it will come in the degree lower, and it will create something line. There is one method. Another method is that instead of plotting the graph on the x and y axis, if I put the graph on the x square and the y square axis in the same dimension, it again also it will separate in the 2 different.
It's not just plotting. It's not for you to visualize. It's you're transforming the data so that you can apply the traditional k-means algorithm on it, so that the data becomes separable. It's just not about plotting or visualizing things, right? I hope that point is clear. We are not just trying to visualize things. We are actually transforming our data, right?
So okay, so we'll do one thing, ma'am. So it will become here long discussion. So I will solve this.
Yeah, that will be good. So whatever you are suggesting, probably show that in a detailed manner, so that we can talk about it. Okay.
Yes.
All right. So where were we?
Ma'am, could you please explain what is Voronoi region?
Okay, so the region that is formed by the half spaces is precisely the Voronoi region. These are the regions. So this is, you can say, Voronoi region 1, Voronoi region 2, and region 3. How are these formed? These are, so basically you would have means of these clusters, right? For every mean you have a cluster, right? Sorry, what I'm saying. For every cluster you have a mean, right?
Yes, ma'am.
You join these means, okay? And then exactly the middle point, put a perpendicular line there. That will be the separator for these 2 means, or you can say for these 2 clusters. So here we have 3 clusters and corresponding 3 means. So you join these means and put a perpendicular line exactly at the midpoint. So these are the lines that we are getting. These are the half spaces that we are getting. So intersection of half spaces is what is giving us the three Voronoi regions. Any point falling in this Voronoi region will belong to cluster 2, and any point falling in, let's say, this Voronoi region will belong to cluster 3, and so on. Okay?
Okay, ma'am.
All right. Next question. Yeah, second one we have done. Third question is, K-means can efficiently cluster data points that are not linearly separable. We just now spoke about it. It cannot cluster data points that are not linearly separable. Okay, this is incorrect. It cannot, yeah, second option is correct. And we also talked about it. Kernel K-means is used to cluster data points that are not linearly separable. So these two will be the correct options. Which of the following is true with respect to optimality of clusters? K-means may not guarantee obtaining the optimal clusters, but there are other techniques that guarantee optimal clusters. What do you say about it? Yes or no?
No, there are no other techniques.
Correct. We spoke about it. It's an NP-hard problem. We cannot expect any other technique that might be able to produce optimal clusters, because that would require exponential number of comparisons. So even if there is any other technique for clustering, there are definitely other techniques other than K-means, which can be used for clustering the data points. But even they will provide us a solution which may not be optimal. Okay, even those techniques cannot guarantee that their solution will be optimal. Getting optimal cluster is an NP-hard problem. So yeah, this is the correct option. Okay. Now moving on. To obtain good clusters, how should the initial means of clusters? So let's talk about the initialization of means, which is an important thing. Means should be as far apart as possible. So how are we assigning means so far in K-means?
In K-means, it was random.
Right.
Completely.
Right. So K-means, in the first step of K-means is that we randomly assign the data points, and they could be probably close by, or they could be far apart, or there could be any random allocation. But what is a good placement? Let's talk about that. Mean should be as far apart as possible. They should be as close to each other. A random placement is the best placement. What do you say?
As far apart as possible.
Right. They should be as far apart as possible. Why? Because we have a chance of settling into a global optima. If that is the case, there is a chance. Okay, there is a chance that so if the initial means are close by, we might settle into a local minima. But if they are far apart, we might get good clusters. Okay. So K-means plus plus. So we know that K-means does it randomly, and random may not be a good idea. So we have another variant, which is K-means plus plus, which initializes the clusters. How does it do? Any idea? Anybody would like to comment?
First of all, assigning the score and taking the probability, and highest probability will be selected as initial means.
Highest probability will be okay.
But ma'am, in this I have the doubt that let's suppose there are K means. That in the lecture, sir have selected initially randomly. Sir has said that let 5 of the means have let the 5 means are assigned to it. Now next will be assigned in such a manner, like I said, probabilistic manner. But the initial 5 was I think assigned randomly. Is it right? Is I'm right on the
Initial 5 are assigned randomly is what you're saying? No.
Yes,
The
in
first,
lecture.
no, there's some misunderstanding probably that you have developed on seeing the lectures. So I think what sir is saying is first mean will be assigned randomly. Okay? First mean. You have to start somewhere. First mean will be assigned randomly. Then,
yes, ma'am. That means if k are there, then only select one mean as random.
Yes.
And next will be selected by the same probabilistic method.
Yes.
Okay.
So basically, in k means plus plus, we spend a good amount of time in the first step itself, which is initialization of cluster means. In k means this was being randomly done, but in k means plus plus, so everything else will come later on, whatever reassignment and change of cluster and so on, that will be same, will come later. But in the very first step, there are some, please note, there are many iterations that take place here. This is not a one-step procedure. There will be certain iterations that take place here. And how many iterations will take place here? Anyone? Think and tell me.
Yes, ma'am. Can you ask once again?
All right. So revisiting k means, what were the steps of k means? First step is initialization, right? Which is randomly done. Second, and then you start with some number of iterations. In each iteration, what you do is you calculate, you assign the elements to these closest means, and then you recalculate the means, and then you keep doing that, right? That's what happens in a number of iterations. Let's say, iterations I goes from 1 to t. The first step is initialization, which is done randomly. This is a one-step procedure. However, in k means, this initialization is not a one-step procedure. This initialization is done across several iterations. Before the reassignment and everything, this thing is same over here as well. The only difference that comes in is the first step, which is initialization. So initialization is done across several iterations. Okay?
Yes.
So yeah, my question was, how many iterations should take place here?
Means after the assigning of only the first mean, there will be iterations. Means every point will be computed with the first mean, and maximum probability will be selected in such a way that there will be many iterations in only in the initialization step as well.
How many iterations? Exactly k iterations. Or if you are keeping this aside, initially the first mean is assigned randomly, then after that k minus 1 iterations will take place. So let me give you an example to make it clear. So in k means plus plus, we have to assign the means initially. First mean, like I said, will be assigned randomly. After this, there'll be certain iterations, and in each iteration, you get one more mean. You run iteration 1. I'll explain you what we do in each iteration in a while. So in iteration 1, you do something, you get the second mean. Now you have two means. In the next iteration, you get the third mean. Now by this time, you have three means. In the next iteration, you get the fourth mean, and so on. So let's say in the k minus 1 iteration, you get the last kth mean. Once you get all the means, you will start the k means as before. Is that clear?
Yes, ma'am.
Okay, now what happens in these iterations? So let's say this is the random first mean that we chose randomly. Now let's say there are some data points. Let's say these are the data points. What do we have to find? We have to find the next mean, mu2. So what we are going to do is, we will compute the distance of each data point mu2 is what we have to find out. For each data point, what we are going to do is we will compute the distance of each data point from the mean that we have already chosen. Okay. Let's say this is 1. Let's say this is 2. I'm just giving some, let's say this is 3. Let's say this is 3. Let's say this is 2. Let's say this is 4. Okay. These are actually square distances that we use. Assume that these are square distances, or maybe I'll square them up. Okay. So let's say these are the distances of each data point from the mean that has been already chosen. Now these distances will be taken as the scores for each data point. So these are the square distances that we take. So this will be 4. The score for this data point will be 4. The score for this data point will be 16. The score for this data point will be 9. This will be 9. This will be 1. This will be 4. These will be the scores for these data points. Now, in k-means, which point we choose as the next mean is the point whose distance from the existing mean is the farthest, is the maximum. Okay. So this is the point whose distance from the existing mean is the maximum. So this point will not be chosen, please note. The probability of this point getting chosen will be the highest. Now these are the scores. Now how do we convert them into probabilities? You sum these up. 16 plus 4 plus 4 plus 1 plus 9 plus 9. How much this is? 9. I think this one, please cross check, whatever that is. Right? So let's say 43. So we basically normalize these scores and convert them into probabilities by writing 16 divided by 43, 4 divided by 43, 4 divided by 43, 1 divided by 43, 9 divided by 43. So these are the probabilities with which these points will be chosen. Now this very point you see has the highest probability of getting chosen as the next mean. So there is a high chance that this point will be chosen as the next mean, mu2. Is this clear so far? Any doubt?
Yes, ma'am. That I want to ask is that it is not a natural probability. Means that this is not a randomization. This is making it a probabilistic in nature.
It is probabilistic. It is not random. Only the first point is randomly assigned.
Yes, ma'am. That I understood. But we are forcefully making it probabilistic. But instead, we can be directly selecting this 16 number.
Yeah. So like sir has explained this very point that we don't want the algorithm to be deterministic. We want.
Yes.
Yeah.
Yes, ma'am. Yes, ma'am. That's why I'm saying we are making it
probabilistic. Correct. We are making it probabilistic because we may not guarantee that even if we choose them deterministically, we may be able to get the best optimal clusters. We cannot guarantee that. So that's why we keep it probability based, right? Which has a high chance, which has a good chance of giving us good clusters. But see, we are not sure whether if we take this point as the next cluster, we will end up with an optimal, configuration.
Yes,
we will end up in a global minima. We cannot say that. So that's why we try to convert into probabilistic one than a deterministic one. Now, is this clear so far?
Yes, ma'am.
All right. Now let's say we have chosen this mu1 and mu2, and now we want a mu3. Would anybody want to explain me what will happen now? How do we choose mu3?
Mu3 again will be chosen in such a way that this time there will be two comparison for a single point.
Very good. Yeah.
So we will select minimum and all the minimum will be collected, and in that minimums the farthest will be selected so that it will remain farthest from all the points.
All right. So let me repeat this for others. So we have now mu1 and mu2 and we are looking for a mu3. Now what we will do is for each data point, please manage the clutter that is present here. I don't want to redraw. So just consider this point, and this point, and this point. So these are the candidate points. This one has been already chosen as a mean. So we have 1, 2, 3, 4, 5 candidate points. So what we are going to do is we'll find the distance of each point from each mean. Please note this. Okay, this point, this mean, this mean. Similarly, this point, distance from this mean, and distance from this mean. This point, distance from this mean, and distance from this mean. This point, this mean, this mean. I hope you get the point. It's quite cluttered. So for each point, we will check their distance from each existing mean. Let's consider this very point. Now, there are two distances now associated with this point. Let's say D1 and D2. We will keep a track of the minimum of these. Please note this, minimum of these. Let's say D1 was 2, and let's say D2 was 3. So we will keep a track of the minimum of these, which is 2. So we assign a score 2 here. It's a square distance, so the score will be 4, please note. All right. Let's look at this point. This point has some distance, let's say 1 from mu1, let's say 5 from mu2. We keep a track of the minimum of these distances, which is 1. 1 square is 1. This is the score for this point. Let's take a look at this point as well. The distance from mu1, let's say, is 3. The distance from mu2, let's say, is 5. The minimum of these is 3. 3 square is 9. So the score for this point is 9. And so on. Okay. Again, you will normalize them, which means you will convert these scores into probability, and you know how to do it. Just sum them up and you get the denominator, divide whatever that is. Divide all the points by that denominator and you get the probabilities. These will be the probabilities by which these points will be chosen as the next mean, mu3. So precisely what we are doing is we are looking at the point, that point, let me write this down, this is important. That point will be chosen as the next mean whose distance from the closest mean is the maximum. Is this clear to you? There are two things involved here. See, what is our motive? Our motive is to have means which are far apart from each other as much as possible. Okay. So now the point, which is the point whose closest distance, or you can say whose distance from the closest mean is a good one, obviously will have a more distance from the other mean. So this point, this point, look at this point. Its distance from the closest mean is 9. Square distance from the closest mean is 9, which means its distance from the other mean is even more than this. Whichever point has more such value, which means this point is the maximum far apart point that we can get in this data set. So it is a good candidate to become the next.
Excuse me, ma'am.
Yes.
Yeah, ma'am. How did you get that 9, ma'am? I couldn't understand.
Okay. Yeah, it's a little cluttered, but let me repeat. So this is a point, right? I will look at the distance of this point from both the means, mu1 and mu2. let's say the distance of this point from mu1 was 3 and the distance of this point from mu2 is 5. Okay.
This 5 is, we are assuming it?
No, we will calculate in practice.
Okay.
I mean, here I'm
Okay.
not calculating because
Yeah,
for
yeah.
that I need
Got it,
coordinates.
ma'am.
Yeah. So
Got it.
minimum of these is 3, because if we keep track of the minimum distances, we know that there is no mean which is closer to this point. I mean, I hope the rationale behind looking at the minimum distance out of these two is clear to everyone. Please ask me if it is not. So 3 is the minimum of these. Square distances is what we have to look at. So 9 is what we get as the score for this point. Similarly, we get the score for all the points. Okay, is that
Yes,
clear?
ma'am. Yeah,
Then we
thank you, ma'am.
normalize. Yeah, then we normalize and then we use these values as the probability scores for getting chosen as the next mean. All right. I hope that is clear to everyone. Let's look at the question that we were looking at. Where were we? Yeah, third question. During different iterations of the initialization step, k-means plus plus assigns highest probability to those points to be chosen as clusters means for which the closest cluster mean is the farthest, right? Is this clear? The first option will be the
Yes.
correct one. All right. Due to a smart initialization of cluster means, k-means plus plus is able to produce optimal clusters. Yes or no?
No.
Good.
No, because
No,
we
you
may
want
or
to
may
change
not.
your answer?
No,
Yeah.
we may or may not.
Yeah,
Again,
we may or may not. Correct. Yeah, we cannot guarantee. Correct. So this is false. Let's move on.
Ma'am, but in question it is saying that okay.
Okay, no,
Able
I know
means-
you're right. The question should actually say that guarantee. Yeah. It is able, but I mean not always. So it is not guaranteed. Yeah, it will be good to reframe the question. K-means algorithm automatically determines the. We have. Am I audible? Hello.
Yes, ma'am.
Yes, ma'am.
Okay. Yeah. Where are we? Yeah, k-means algorithm automatically determines the value of k. No, it doesn't, right? We have to provide the value of k. So this is false. Which of the following is correct with respect to the value of k? The value of k should be as large as possible. The value of k should be as small as possible. Anyone? The value of k should neither be small nor be very large. What do you say?
Neither be this third option, not very
option.
large, not very small.
Okay, why?
Because if it would be large, that means let's assume k is equal to n. then that is same data means what is there is no clustering in that. That means the cluster the value will be 0 of the objective function. So there is no meaning. And if k is 0, k is 0, then
k is 0 means what do you mean by k is equal to 0?
K equal to 0 means there are no partition.
And what do we mean by k is equal to 1?
K equal to means we are making two partitions. Means two clusters, basically two clusters.
K is equal to 1 means we are making two clusters, is it? So k is equal to 2 means we are making 3 clusters, is it?
Yes, yes, that's okay, ma'am. I made mistake.
Yeah. K is equal to
K
1.
means,
K means number of clusters. K is equal to 1 means everything in the same cluster.
Yeah.
Okay. Let's say n is the number of data points. If you take k is equal to n, what will happen? Anyone? So one situation is, so these are two different scenarios. I'm trying to take the same points. So one scenario is k is equal to 1. Every point is in one cluster. The other scenario is k is equal to n, which means every point is there in their own clusters. right? This is the other situation. Okay. Now, what is our motive here? Anyone? What is our motive here?
To minimize the
Motive
objective
is that
function.
Sorry?
To minimize the objective function
Correct.
to a certain limit, not have it 0.
Certain limit, is it? What is that limit?
I mean, there's a trade-off, right? You shouldn't have it equal to 0, because then that's a useless cluster.
Okay.
yes, that's right.
Minimize the objective function. So far what we have been discussing is our objective is to minimize the value of the objective function, and what is the objective function? The distance from the mean, the distance of each data point from its mean. Now, if you look at the this cluster, the distance from the mean, which is the point itself, will be 0, right? Look at this cluster, the distance of this data point from the mean, which is itself, will be 0, and so on, right? So what will be the value of objective function here? 0. On the other hand, this is the situation. There will be some mean of these data points, and there will be some distances of those data points from the mean, and you square them up, sum them up. So there'll be some value of objective function. Some good value of objective function will be there, right? And we've been, so far we've been saying that our motive is to minimize the objective function value. So isn't this a good situation? No?
Then there is there is no clustering, but in this, then means what we are talking about.
Right, very good. So there's nothing that we're learning, right? What is our object? Our actual objective is to learn some patterns in the data, and in this particular case, the patterns are the clusters present in the data. When we make k is equal to n, we are basically not learning anything. Again, if we are taking k is equal to 1, we are not again learning anything. So the value of k should be somewhere between 1 and n, right? That's what we are looking for. Now, what should be that k value is what we are not sure. And sometimes domain knowledge tells us that these many should be the clusters. Like I gave an example of the grades. Sometimes the domain will tell you how many clusters we are looking for. But sometimes that is not possible. So we try out different values. But whatever different values we try, please can somebody mute? There's some noise. But whatever different values that we are trying, they should not be 1 or n, right? So I hope that is clear to everyone. So it should not be very small or very large. If objective OBJ represents the value of objective function and P represents penalty. So what is this penalty that we are talking over here? So I gave you an example that if k is equal to 1, the value of objective function will be very large. On the other extreme, if k is equal to n, the value will be very small. So as you keep increasing the number of clusters, the value of objective function will increase or decrease?
Decrease. If we
Right?
increase the
As you keep increasing k, what happens to the objective function value? It keeps, tell me?
decreasing.
Decreasing. It keeps decreasing, right? So since so far our objective has been to minimize this, but we do not want k to be high as well. Like I told you here, we don't want k to be high because that way we lose the patterns. So we need to apply some penalty for increasing the k value, right? So our final, you can say, final objective function sort of becomes the objective function value, which is the distance from the means, plus some penalty we put as an additional term. This penalty is for increasing the value of k. So if anybody has any idea of regularization, if you are aware of, although it will come later on, I think in week 6, but regularization is also something like this. Some penalty we give for the weights. If the weights are increasing, we apply some penalty. That's what happens in ridge or lasso. I mean, that's a similar setup. So I'm bringing it up, but don't worry, it will come in week 6. So this penalty we apply. So more the value of k, more the penalty. It's like that. All right. So we want that objective function which is, taking care of both these things. So that's what we look for. So here the best value of k will be that for which obj plus p is minimum. Okay, so this should be the correct option. Next is, which of the following techniques helps in fixing a suitable value of penalty? To fix a suitable value of penalty, so we don't know, right? As k increases from k to k plus 1, one cluster has increased, how much penalty we should put? We cannot just like that determine. So there are some techniques for that. AIC and BIC, these techniques, you don't need to, at this stage at least, you don't need to get into the details of these two techniques, but just know that there are some techniques that can help us fix the right value of penalty. And this third option is something that you should know about. This is a method that one can use to find a suitable value of k. So we've been talking about the fact that we may not be sure about what is the right value of k. So what we do in practice is, for the given data set, we try out different values of k, right? In practice, you are a data scientist, some data has been given to you, and you have to find the patterns in that. You're not sure which value to k to use to start with, right? So you try out different values of k. So, so what you might do is, on the x-axis you have, let's say, k. On the y-axis you have the value of objective function. As you keep increasing the value of k, let's say 1, 2, 3, 4, 5, 6, some values of k you try. This is objective function. Can you tell me what would be the line like, the plot like? As you keep increasing k, what will happen to the objective function?
It's a downward slope, decreases.
Correct. It will be decreasing. It will not be a straight line, of course, but it will be downward. Now, we might want to take a look at the shape of this line. So for k is equal to 1, getting back, when k is equal to 1, there's a good value of objective function that you have, right? So some, let's say this much value of objective function is what you found. For k is equal to 2, you reduce the clusters, you increase the number of clusters. So these points are now in this cluster. These points are in this cluster. They would have a mean here. They would have a mean here. So obviously, the objective function value is going to reduce, right? So we will have a reduced value here. And for, let's say, k is equal to 3, you get this value of objective function. And then as you further keep increasing the value of k, it will sort of start reducing linearly. So if you plot this, something like this, it will be there, and something like this, right? So this is kind of an elbow that you are looking for. Elbow is a point after which the reduction in the value of the objective function is more or less linear. Okay, so that is the point that you're looking at, and given the data, you would see that there are some patterns that you would be able to observe at k is equal to 3. But after that, it's just like this thing, putting points in their own cluster, and hence the values will keep reducing. So values will keep reducing, definitely, that we know, but in which manner are they reducing is what we will want to take a look at by this elbow plot that's popularly called. So here you see the value reduced because there was some pattern actually. Let's say the data was like this and like this. So when initially you put them in one cluster, there'll be some good value of objective function, this one, let's say. When you put them in two clusters, the value will suddenly reduce. Why? Because you have captured the clusters present indeed, because these will be the clusters, and the distances you will see, because they are actually part of two different clusters, the distances will indeed reduce as compared to the previous case where this was the cluster and these distances were way too high. I mean, it's getting a bit cluttered, but I hope you get the point. So when the moment you go from k is equal to 1 to k is equal to 2, you will experience a good reduction in the objective function value. And in case there are more such patterns present in the data, you would observe furthermore reduction. But if there are no more patterns, this will linearly reduce, because every point will sort of be a part of their own cluster ultimately. So k is equal to 3 is going to be sort of a value that you would want to continue with. Is that clear?
Yes, ma'am.
All right. So that was about the activity questions. What I'll do is, in the next class, I'll start off with the practice assignment questions, and then we will take up the programming questions. So yeah, that's how we will cover the next one. All right. So shall we close it now? We'll see you in the next session, which is on Saturday.
Yes, ma'am. Okay.
All right.
Yes, thanks, ma'am.
Okay, thanks everyone. So it was a good interactive session. So practice well. Take care. I'll see you in the next one. Bye.
Thank you, ma'am.